We now proceed to examine the D operator and how the D operator makes the writing of certain equations simpler. And we have to understand the full significance not only of the D operator but also what is meant by, for example, the inverse D operator. We spend some time discussing these few basics and then see that the D operator has to be used with a caution. There are certain cautionary remarks on the algebra of D operators we will see through an example. So, first step is, if the dependent variable is y and the independent variable is x, then D stands for ddx. It is an operator and is equal to differentiation with respect to x. When we write d of y, in this context it would mean is the operator ddx operating on y, and that's nothing but dy dx. When we write once again, say for example d square y, or I will not say implies, I will give a definition to it. D square y and higher powers of the operating on y, how they have to be interpreted. So let's say d square y, what does it stand for? D 2y. That is the very correct way of saying, instead of saying d square y. Although we might say loosely this is as d square y, but actually it is d 2y, and that means d operating on d of y. In other words, this is the operator d operating on dy, which is, so this is nothing but ddx operator operating on dy dx. That takes us to d2y dx2. Similarly for higher powers of d. So in other words, if we write d superscript n y, it stands for nothing but dn y dx n. So with n as 1, dy is just dy dx, and so on. So this is one very important operator we introduced, and we will see how we can write our differential equations using the D operator. Let an equation be second order with constant coefficients. So we will write something like this. Purposely taken a function that is not defined here, but that on the right hand side is a function of x. So the equation we have here is a non-homogeneous equation. The homogeneous equation would have been the whole left hand side equated to 0. Now, using the D operator, the equation can be cast into d square y d2y minus 3 dy plus 2y is equal to a function of x. In other words, this simply translates to d2 minus 3d1 plus 2 operating on y is x, function of x. Now once we write this in a simple way, the first step to the solution will be we get the auxiliary equation, and that by inspection turns out to be m square minus 3n plus 2 is equal to 0. The auxiliary equation is m square minus 3n plus 2 is equal to 0. This implies n as 1 or n as 2. In other words, the complementary function is c1 e to the power of x plus c2 e to the power of 2x. But we will focus more on the uses of d here and not right now present any method of finding the particular solution by the d operator method, which will be reserved for a different lecture. Now, the caution part that I was talking of is as follows. What is the meaning of one by fd operating on a function of x? In other words, what is fd minus 1 operating on function of x? This has to be assigned a clear value, a clear meaning. In fact, not a clear value, but a clear meaning. Now, let us take that an equation has been written down in its d-reduced format. So, like for example, we just written down d squared minus 3d plus 2 y is equal to x of x. We just did that. Now, if we are willing, we can call this the particular fd here. So, fd operating on y is equal to x function of x. This is capital, this is small, this is the independent variable, and y is the dependent variable. So, from here, one can write y is equal to 1 over fd operating on x. The question is, what does this mean? What does this mean? So we will take this up separately and give a meaning to 1 over fd operating on x as a function of x. Take it up on top. The meaning is 1 over fd operating on x, supposing it generates a new function, let's call it x sub 1, not the derivative. The meaning is that this function x1 is such that when operated by fd will lead to the original function that was on the right. So in other words, we can write that when fd operates on 1 by fd x, then we get fd operating on x1. Now we can just cancel these two as if they are, the same quantity, and x is nothing but the fd applied on x1. So that gives a meaning to 1 by fd of any particular function. We'll take a simple example and see how we can calculate simple cases. In fact, this leads us to one very important formula for the value of 1 over d minus a. Let's see. What is the meaning of 1 over d minus a applied on x as a function of x? So we have to give a meaning to what is 1 over d minus a applied to any function of x. We start by saying, let us assume that 1 over d minus a capital X of x is nothing but y. Now this implies that d minus a operating on y is equal to nothing but x as a function of x. Now what is this? If we break it out, this implies dy dx, d operating on y minus ay is x as x. We log out this part and carry on the work a little on the upper part of the box. Now if one recognizes this equation, it is a linear first order equation with constant coefficients and needs an integrating factor to integrate. In fact, the integrating factor here is e to the power of the required IF e to the power of integral minus a dx, which is e to the power of minus ax. Remember, there is a very standard equation, dy dx plus py is equal to q, where p and q are functions of x or constants. Now the integrating factor here is e integral p dx. So comparing these two equations, we have written the integrating factor as e to the power minus ax. So once we multiply by this integrating factor, so multiplying by the integrating factor, we get e to the power of minus ax dy dx minus a e to the power of minus ax y is equal to e to the power of minus ax x as a function of x. Now clearly the left hand side is the d dx of y into e to the power of minus ax. In other words, Clear? Or the next clear step is y e to the power of minus ax is integral of e to the power of minus ax x with respect to x. So our friend y which we need is nothing but, last thing we can write on top, we need our friend y in terms of x. So y as a function of x is e to the power of ax integral e to the power of minus ax into the function that is on the right of the equation. So this is significant of what is the meaning of 1 over d minus a, and a can have any value, 1 over d minus 2, applied on any function x is e to the power of 2x, e to the power of minus 2x, x as a function of x. So if a were to be 2, just a typical value, you can take 1, 2, 3, anything. If a were to be 2, then y would be e to the power of 2x integral e to the power of minus 2x x to the power of x as a function of x. I will extend this by one more simple situation in which the example will show we can take complex values of a. Then we will conclude this discussion. Suppose we need 1 over d square plus 1 to operate on e to the power of 2x. Any function, in fact it can be any function. Now, we will do one thing. We will write this as being equal to 1 over 2i, 1 over d minus I minus 1 over d plus I operating on e to the power of 2x. In other words, this is 1 over 2i is a constant, 1 over d minus a operating on e to the power of 2x minus 1 over d plus a operating on e to the power of 2x. So, keeping this ahead of everything, let's first see what is 1 over d minus I operating on e to the power of 2x. 1 over d minus I operating on e to the power of 2x is nothing but e to the power of ix integral e to the power of 2x. This is your capital XX into e to the power of minus ix. Here one can use the Euler equation e to the power of ix is positive to I sin x, and a similar treatment for this. In other words, these kind of factors, even had it been d square plus 3, it is d plus root 3i into d minus root 3i. So that can be, complex numbers can be invoked. That is what I am trying to say, that there will be an answer which will just come out in terms of real values and no i's will be present.